All right, hello everybody. Welcome back.
Hi.
Good afternoon.
Afternoon.
Hi.
Afternoon. That's right. It's good to know. You know, I have no windows in my office, so it's hard to tell what time of the day it is, or whether there's a storm going on outside. All right. Let's see. Jada, are you here?
Yes.
Such excitement. Great. Taylor.
Here.
What happened, Jada?
I just woke up like 20 minutes ago.
Isn't it brilliant? Start a day with statistics. Elliot.
Yeah, I'm here.
Marco. Ava. Oh. Robert.
Here.
Leslie.
Here.
Yasmin.
Here.
Ariana.
Here.
Yuzhan.
Hi, I'm here.
Moranke.
I'm here.
Delia.
Here.
Kaylin. Wei.
Here.
Chansey.
Here.
Nice. Sienna. I do see you on the screen, so text me if, okay, there I see you. Okay. Zach.
Here.
Okay. Diaz.
Here.
Sam.
Here.
Okay. Oni.
Here.
Gloria.
Here.
Nikki.
Here.
Ashley.
Here.
Lucas.
Here.
Wendy.
Here.
Okay. Last call for Kaylin. No? Anybody know what's up with Kaylin? And then Ava, are you here? No. Okay. And then what about Marco? Is he here yet? Okay. Ashley, you're 18 now, right? Congratulations.
Yeah. Thank you.
Is that like considered an adult in America? Is that how we do things?
Yeah. Yeah. I was actually able to enter a pool place for my birthday. To play
Nice.
pool.
There you go. Welcome to adulthood. I think. I don't know. I'm pretty old and I don't feel like an adult yet, so we'll see.
Hey, Professor, I'm here.
Marco, you're here. Who else just logged in? Is that by any chance Ava and Kaylin? I do see Ava.
Hi, I'm here. I'm sorry.
Okay. What about Kaylin? We here yet? No? Okay. All right. All right. Welcome back. Let's see. Yes, let's start with some reviews. What I'll do in terms of kind of just like asking you guys, no, Ashley's birthday was on Sunday. I'm just saying she turned 18, so now I'm congratulating her into adulthood. It was already in the past, but anyways, belated. I remember we having this conversation. So I was like, how young are you guys? So young. What am I doing? Okay, so I'm gonna share my screen and we're gonna just kind of do a problem together, which basically kind of covers some of the concepts we did last week, instead of just kind of asking you guys what we covered. Okay, so let me zoom into this too, so you can guys can see. And it's actually from problem set 5 that you guys are gonna do by the 23rd, 11 a.m. or something like that. So I'll share my screen. So maybe get your Google spreadsheet out, or like a paper pencil and Google spreadsheet, because that will always help. So let's start with question 4 as it's marked on mine. It's basically gonna be pretty much exactly the same question you will do in problem set 5 if you haven't done already, except the numbers are probably gonna different, which you guys know at this point. And I am aware that you guys been getting these notifications that problem set 4 and 5, the deadline has been past due. That's not correct. Apparently Blackboard has been going crazy lately because, you know, so many of us are on it and it just can't handle the foot traffic. Because that's just not correct, right? I checked it today too, and the deadline is on the 23rd at 11 a.m. or something like that, okay? So you're not late for anything. You still have a few days, but they are due Friday, okay? So let's try a question together. So the mean daily production of a herd of cows is assumed to be normally distributed, right? So this is important. It's always important to know, because that basically means we can calculate the z-score. Well, you can always calculate the z-score, but we can actually use the standard normal curve, meaning that we can also use norm as dist to figure out the area under the curve, which is probably where it's going, right? Okay, so normally distributed, it's great information to know. And we have the mean of 31 liters and the standard deviation of 4.8 liters, okay? Important information. So one of the things you might wanna start doing, which I'm gonna do also on my piece of paper, you're gonna draw a normally distributed or bell-shaped curve, and you're gonna mark the mu and the standard deviation, right? So in the middle, I'm gonna do a dotted line, and I will do 31 liters, right? And then I'll say the standard deviation is 4.8 liters. So something like, where's the camera? Something like very simple like this, right? I'm gonna make a bell-shaped curve, smack down in the middle, I'm gonna label the mu with 31 liters, and then on the corner somewhere, I'll say the standard deviation is 4.8, right? I could, because it's normally distributed, I could do what should be your next natural thing you should wanna do, where is I like kind of label like 1 standard deviation away, 2 standard deviation away, and 3 standard deviations away, like the dotted lines, right? In both directions, right? And then I can, on the right side, I can add 4.8 and another 4.8, another 4.8, and I can like label those things. And you can go ahead and do that if you want, but also you can wait till you finish reading the question to see if that's even necessary, right? It could be necessary, it might not be necessary, it depends on what it's asking. Okay, so now I'm gonna go, what is the probability? So when you see the word probability, what should you guys immediately think? Who knows? See the chat.
Fractions.
Fractions, okay, kind of. I mean, we are getting percentages, which is basically, in a way, it could be fractions because it's out of 1. But what in particular are we thinking about when we hear probability? It's the area under the curve is where we're going. That's what you're thinking. What is the chance that? What is the probability that? What is the percentage that? Whatever, if any of those things appear, and it's always gonna be that, you're gonna immediately think, we're gonna be talking about the area under the curve, which is kind of like the only type of question we've been really dealing with, okay? So what is the probability that daily production is between 35.2 and 42.1 liters? Okay, so go ahead and do this. I'm gonna ask you guys to submit a few things on Blackboard, so I know that all of you guys are actually doing this by hand or doing it in Google spreadsheet. So I'm gonna create something in Blackboard right now. So the first thing so basically the answer is what you're gonna input, but along the way, I'm gonna ask you a few other things. So the first thing would be, well, I won't tell you. You guys, so solve this problem now, and then along the way, you will have to do a few things. Okay, so if not, write down everything first, that the mean is 31 liters, and then that the standard deviation is 4.8 liters, and then that we are looking at the probability, so basically area under the curve, between 35.2 and 42.1 liters. The reason why I'm telling you to write it down is because I'm gonna start unsharing my screen in a second so I can create this thing in Blackboard that you're gonna submit. Okay, so write it all down. 31 liters as the mu, 4.8 liters as the sigma, and then knowing that this is, you are looking at the probability between these two numbers. All right, you guys all got it? Okay, so I stop sharing. All right. Okay, you guys are 308. So content. Oh, error. Blackboard is having such a hard time today. So maybe you guys can help each other out. What's the first thing you probably should do when that question is asked, guys?
Don't we have to add and subtract the standard deviation on both sides?
Yeah, it would be nice to actually, like I was hinting, label those 1, 2 standard deviations away by using the standard deviation, right? To see where 35.2 and 42.1 would lie. So that would be the first step. Very good. Very good. So start with that.
Will the next step be to find the z-scores for each one?
Yes, I would think so.
Okay.
Very, very good. Maybe I guess you guys don't even have to like label it on the graph and directly find the z-scores first too. I guess you could do that.
Professor?
Yes.
Sorry, I don't know what happened with my computer. I was not able to see the question like that you were presenting on.
Okay, so I'll put it right in the chat. So it's 31 liters as mu, 4.8 liters as sigma, and then we are looking for probability between 35.2 and 42.1. All right, all the information you need is in the chat, okay? Okay, content. Assessment. Let's put that in. Distribution. Class sample. Right, so I want to make that due date today. Okay, so basically, this is what I'm going to ask you guys, and this will obviously tell you how you're kind of supposed to answer this question, if you will. And everybody has to kind of go through this anyways. So make sure number 1, 2, 3, 4, 5, each, you know, you will have an answer to it. And then I will, then you'll go to Blackboard, content for normal distribution, and it's all the way on the bottom. But I will also type that in the chat too. you will submit these answers at That's where you're going to submit all those answers. And I'm going to check that all of you guys actually submitted. So this is like what we practiced last class, where instead of starting with a standard normal curve, we're going to start with a regular normal curve with the mu and the sigma. You turn that into basically a standard normal curve by using z-scores. Then you calculate the areas under, and depending on whether it's asking left tail, right tail, or area in between, you know, will be a little bit different. This obviously is the last kind where you're looking at the area in between. And then that will be kind of like a practice for you, so that when you do problem set 5, you have an idea of what's going on. And then there's the backward problems. Guess I don't have an example of that. Let's see. Marco, it's right above your question. You will submit these answers at, and I wrote the pathway for you. Is that not clear?
How would we submit them? Like through a Google spreadsheet? Or
Isn't there a place where you can just enter, like there's a text box when you click on it? Usually in Blackboard.
yeah, I see it.
Just type it in there directly. You calculated all of those, answered all of them, and submitted in Blackboard, then text me in the chat that you're done.
Did you want them in percentages or decimals?
Oh, that's a great question. So for number 5, please put that in percentages. Great question. Yes. Great. Some of you guys are already done. For those of you guys who are done, please try out this question that I'm going to type in the chat.
But I'm trying to find 3 and 4.
Okay. So did you find 1 and 2?
I think so.
Okay. So what did you get for number 1? Let's see if we all agree as a class.
If I did it correctly, 87.5.
87.5 for number 1.
Yeah. No.
And then for number 2?
2.31.
31, is that what you said?
2.31.
Okay, actually, I haven't done it. Let me just do it really quickly. Do the class agree? I should have done that. Let's see. So 31. So for the first one, 35.2 minus 31 divided by 4.8. Yep, I got 0.875 though, not 87.5.
Okay, so I got that at first, but I multiplied it by 100. I didn't know if we were supposed to do that or not.
No. We're not dealing with, so number one, guys, z-score is not a percentage, right? It's just the z-score. And the equation is that you take the x value that you're given from the problem, you subtract it by the mu, and you divide it by the standard deviation. As number 1 and 2, we are not dealing with any percentages. This is just a z-score. Okay, so what you get as after you plug it in that equation, that's exactly as it is. It stays there.
Okay.
So number 1 should be 0.875. Did people get the same?
Professor,
Yes.
I'm a little confused on how you found that. I'm sorry, it's just taking my brain a little to.
Okay. Let's go to. Okay. Chapter 13 is called Z values. Let me put that in the chat. Okay, and this is, you don't have to memorize it, but I'm hoping that because we've done it so many times, you kind of remember how to do it. But in order to get a z-score, you're given an x value, and in our case, our x value is 35.2. You're going to do 35.2 minus the mean, which was 31 as given in the question, and then you divide that by the standard deviation, which was 4.8. That's how we got 0.875. If you like plug it in, that's what you'll get.
Okay, yeah, I just didn't see the mu and the sigma, sorry.
Okay, so great. So now, based on that, Jada, can you tell me what you got for number 2?
Okay, so Professor, just making sure, how do we find 3 and 4?
Oh, I mean, okay, so we'll get there, but what did you get for number 2 then?
Oh, 2.3125.
Excellent. Okay, so that's what I got too. Does the class agree? Okay, great. Gloria agrees, Wendy agrees. Okay, so now we're done with number 1 and 2. So now we have a z-score, meaning that we can now use that using pretty much the most used equation we've been using in the Google spreadsheet, which is yes, great. So in a Google spreadsheet, or you can look up the Z table, which is in Appendix A, but it seems like majority of you guys, or maybe even all of you guys, prefer this, which is so much easier, right? You open up a Google spreadsheet, you do equal norm S dist, right? Normal, S standing for standard, dist for distribution. And then to be exact, actually, you'll do norm S dist, 0.875. You'll plug that in and then you'll hit enter. When you do that, which is the answer for number 3, what is that giving us? What number is that representing?
The area to the left of the z-score.
Yes, excellent. Yes, exactly. The area under the curve left to that z-score. Remember, when we're using norm S dist, we are using what's called a z distribution. So on that x-axis, it's all these z-scores. 0 is the middle, and it goes positive on the right side and negative on the left side, right? All these z-scores, 0.1, 0.001, and then negative 1.23, all the numbers. It's a continuous line. And when we plug in that, it's going to draw a line where that z-score is, and any area left to that is what when you hit enter in the spreadsheet, that's what it's telling you. Okay, because remember, the z-score, the z table and this normus dis is always going to give you the left side of things. Okay, that's just kind of like the default. So now we're going to do that for number 3. So you plug in 0.875 and get an area to the left of that. And then you're going to do the same thing for number 4, where you do equal normus dis, but instead now you put in 2.3125 and enter. So you'll get the area left of that z-score in 3 and the area left to 2.3125 in the 4th one. Okay, so obviously that's not the end of it, because we're not getting the left area of each of those z-scores. What we want is the area between those 2 z-scores. And what did I say about area? Can it be negative? I'm
No,
gonna
it
ask
has
you
to be
again, Ava.
positive.
Ava, is this can area be negative? Yes or no?
Yes.
No,
Or-
area
no,
cannot be
no,
negative.
no.
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 Did you get my email?
I got it, yes.
Okay. Area cannot be negative, right? So with those 2 left areas that you got from 3 and 4, in order to get a positive area, Ava, I'm going to ask you again, which ones should be subtracted from which?
The greater one from the least one. What do you?
Well, okay, so greater one minus small, but in English language, if you say from, then you have to say smaller from the greater one.
Oh,
That's
yes, correct.
That's why I
Sorry.
hate English. English is so complicated. But yes, greater one minus smaller one.
Yeah.
But in English, we say smaller one from the greater one, right?
Yeah.
We're subtracting the smaller one from the greater. Okay, good. Which will give you a positive area, an area between those 2 z-score, which is the answer for number 5.
Hey, Professor, I have a question.
Yes.
So for the area, well, when they ask us for the area to the left of number 1 and the left of number 2, do we express that as a decimal or as a percentage?
That's an excellent question. Okay, so that can be either one, and that's depending on what the question is asking. So because number 5 is our ultimate answer, I would kind of keep 3 and 4 as the decimal, and then only in number 5 I'll convert it to a percentage. But to be fair, the way I'm asking in the assignment, I don't ask you anything. So even if you put everything, even including 5 as decimal, technically that's correct, because I didn't specifically ask. But yes, that's a very good point, and I should be careful about that. I should be the one asking you specifically if I want the answer to be in decimals or in percentages. So that's how you would know, because it will tell you.
Okay, thank you.
Great question. Excellent. Okay. It looks like Yasmin and Leslie agree. Is this for oh, that's for number 2. Okay, so what did we get for number 5, guys?
Wait, just confirming for after we did the spreadsheet, what was the answers everybody got? I didn't hear if we all got the same thing.
I don't know if we actually shared it. So let me do a Google spreadsheet. So for Rob, I think what's happening with you with your spreadsheet is, remember in class, because I was giving you guys assignments and there were certain settings that were done, and it was automatically rounding everything up to 1. So don't use one of those spreadsheets. Just start a brand new spreadsheet where there's no settings. Yeah, that probably is. Oh, you wrote the wrong answer. You can submit again. Of course you can submit again. Let me just give me 1 second. Let me just allow multiple attempts. Okay. All right, so Jada asked the question, guys. What did people get for number 3 and number 4? Let's answer that first. What did we get the left tail area answers? Let's check that we're all on the same page. All right, looks like Ariana, Wendy, Zach, Nikki, a lot of people are agreeing on number 3. I also see a lot of agreement on number 4. I think we're very happy with that, right? Excellent. Submission details. Allow unlimited attempts. Okay, So if you refresh your Blackboard, you should be able to submit again if you by any chance got the numbers wrong. And yes, like Yasmin, you can cut off to 3 decimal points, or you can add all those decimal points. I didn't specifically ask you, so any of those answers are correct, okay?
Okay, and just making sure how did everybody get 18% as the final answer?
And as our following answer, it seems like we agree that we got 18%, correct? Nice. Rob, were you able to get a new spreadsheet and actually get the answers instead of it rounding
Yeah,
up?
it's working.
Okay, perfect. Okay, so just moving forward, things like this did happen, remember, in class as well. So when you do the midterm or the problem set, please use a brand new spreadsheet where there's no crazy settings or rounding up settings applied to it, so that you're starting a clean sheet. Yeah. Yeah. All right, excellent. Okay, so I'm glad we did this together. There should be no confusions, right? Z-scores can be negative, positive. Z-score can be 0 as well, right? Z-score is a whole continuous line, right? And the Z distribution is when you think of standard normal curves. Only when we get to the norm S dist are we calculating areas under the curve, okay? Z-score is our intermediate step in order to calculate the area under the curve. How did everybody get 18%? Okay, so Jada, answer me this. You got number 3 and number 4 like everybody did?
I just didn't know we were supposed to add or subtract, but Wendy told me.
Okay. We don't want to add because we're trying to get the area, like the area under the normal curve cannot go above 1 or 100%. So that should be another guidance on whether something should be subtracted or added. But we've never done addition when it came to the area under the curve, right? We only did subtraction. And we do the bigger area minus the smaller area so that we end up with a positive area. Okay, Kaylin is here now. Jada's good. Good. Okay, so I think from all the chats, we are on the same page. We are understanding that percentage only applies to the area under the curve, which is only when you use the norm S dist function. The Z-score is not a percentage, and you're not multiplying 100 or anything like that. Z-score is an intermediary step to get the area under the curve. The norm S dist is always going to give you the left tail area of that Z-score you inputted. Okay, any questions, any confusion still? This is definitely a type of question you might expect on the midterm and the final. Okay, so you do need to know how to do this. All right, any questions about that? And then did everybody actually submit in Blackboard the 1, 2, 3, 4, 5 answers to that?
I'm doing that now.
Okay, great. And then I think some of you guys already done it, but when you're done with that, I'm gonna type it in again. Oops, that's not it. I want you to do one more question. We're gonna do one more together. And this is maybe probably the most complicated one we've done so far, which was the backwards problem, right? It's the same thing we're doing, still involving area under the curve and all that kind of stuff. But now we're just starting from the percentage area under the curve all the way back to the first X value. Okay, so I'm going to type that, paste that question into the Zoom again, the chat again. And so this is our information. So we're starting with area under the curve. I think, let's see. Suppose you have a retail item SKU with a demand on average of 340 units per month with a standard deviation of 80, right? So we got the average, the mu, 340, and then we got the standard deviation sigma, 80. What level inventory should you carry in the upcoming month to assure that you have 95% service level on this term? Okay, so 95% is your area. Yes, we are looking for X. We are looking for that level of inventory that you should carry out, which is for mathematical purposes, we're gonna call it X so that we can solve for X. Okay, so this is the second question that will help us do the review. Okay, so what's the very first step we should do, guys?
Draw our curve.
Yeah, I would draw out a curve, right? It's kind of like all confusing with all these words, right? I'm kind of like a little bit of a visual person. I'm assuming a lot of you guys might be too. So you draw out the curve, and then I'm gonna like label the mu. And then I'm gonna label, I'm just on the side, do sigma equals 80, right? And then after you draw this out, let me just like that's kind of what I did. I'll kind of get rid of the stuff around it so you're not confused. All right, so really simple, right? I just drew something that looks kind of like a normal curve. In the middle, I have 340 as a mu, and then on the side, I just did sigma equals 80, right? Very simple. And then in this case, we're doing X value. So you kind of have to, we're starting with an area. So you're gonna have to maybe, and it might help you, to draw what 95% of the area under the curve would look like. Okay, so go ahead and try that out, and let's see what kind of pictures you guys get. And roughly, I mean, obviously we're not going to be exact about like drawing exactly what 95% of the area is, but roughly. All right, so who's got kind of like it drawn out on their graph that represents 95% area under the curve? Do we do this in an, you can do it in the same spreadsheet that's open. That's fine. You can do it on a piece of paper like I'm doing, whatever you prefer. So who can share on the screen like what they drew to represent 95% under the curve? Oh, it's on your iPad? Ariana, but you can like kind of point your iPad to the screen, can you?
Yeah, I forgot I could do that. This is what can you see it?
Yeah, there you go. I like it. But bring it closer to the camera so that people can see. So I would say that's pretty good, right? It's roughly about 95% under the curve that she drew, okay? So very similar to me. I did this where I kind of estimated that's about 95%, and then I went ahead and kind of draw that line, and then I put X underneath it and then said equal like question mark, because X is what we're looking for. Okay, so this is just, we haven't done any calculations yet. All we did was reinterpret the text question into a visual question. That's all we did, right? With all the information we need. Okay, so that's kind of what we're looking for. Are we all good? All right, so when that is done, and let me know if you're confused and chat me in the chat. So what is a good way to approach this question? What's the first thing we're gonna do? Oh, and I can also do something like this. Should probably add a thing that says in the corner you can see, I said that colored area with an arrow is 95% under the curve, right? So that will be kind of like the full information. All right. Very good. So Taylor's like norm S inv. Inv standing for inverse, right? Very good. Very good. Very good, Zach. All right, so let's go ahead and do that, right? We only learned basically those two things. Well, okay, a long time ago, we did sum, and then we did like, median and whatnot. But really in terms of an actual equation, we did norm S dist, and the other one is norm S inv for inverse,
Oh.
right? Because now we're starting with a percentage and then ending up with a z-score, which is opposite of what we've been doing.
Oh my God. Okay.
Don't, oh my God, guys, this is okay. So remember that you can't put 95 in. It's a scale of 0 to 1, right? So we're gonna put 0.95 in the parentheses for equal norm s inv. So we will do something like, oops. What I typed in the chat. All right, so when you do that in the spreadsheet, what do we get, guys? Very good. Ariana got 1.644. I got 1.64. Yusung got 1.64. Yusung, you're chatting me privately, which I guess is fine. Gloria got the same. Yasmin and Zach also got the same. Great. Okay. So this is what again, guys? What is 1.644? Let's be very clear on what we got. That is the z-score. Excellent. The z-score is now 1.644. Okay, we're not quite done. That was the first step. Now from the z-score or z-value, same thing, we now want to get the x value. So remember the equation that we were reviewing that I said was in chapter 13. We're gonna plug everything in. That's right, Zach. Now we're gonna plug everything in except for the x and then solve for x. Excellent, guys. X minus divided by, okay. So let's calculate that and see what we get for the x. Oh, there's gonna be a fire drill. Oh no, it's moved to 3, so it won't affect you guys. There's gonna be a fire drill practice apparently, guys. There's gonna be like 5 people who exit the building. There's nobody here. All right, Yusung got 471.2. Ava and Zach got 471.6. Well, I guess it's very similar. Let me see what I get. I guess that just depends on how many decimals you included in the z-score, right? So that should be right. Yep, so I got 471.52. So somewhere around you guys. All right. When you got 471.6, 471.2. So what I would do, guys, the reason why the decimal is a little different is because some of you guys, when you got the z-score, you maybe rounded it down or rounded it up. So I would say till you have to go to your final answer, just keep the original number. Like don't round up or round down anything. Try to keep the original answer as far as you can. And then only at the end, round something down or round something up. Because then you'll keep the accurate number as far as you can. And then really why we round up or round down is because we just don't want to write out 10 decimal points, right? Just so it's cleaner. So we do that quote unquote toward the end. So for example, I think Gloria got 1.644853625. If that's what you got, I would try to keep that number as is and then keep going. And then when you get to the answer, then you can cut it off as the instruction tells you to, like 2 decimal points or 1 decimal point or something. Okay. All right. Very good. Up to this question. So you have to be able to solve the question like we did just before this question, as well as a question like this. Does anybody have any questions how you might approach these 2 types of questions? And the other ones are basically kind of similar questions, but they're mostly simpler than this. So if you know how to do this, my assumption is that you know how to do the simpler ones. We're good? All right. Looks like you guys are doing a great job. Okay. So with that, we can finally move on to the next topic, guys. But before that, we'll do one visualization activity, and then we'll move on to the next topic. The topic that we are going to cover today, you might have heard of it. I think it was Ariana or some of you guys did actually take stats in high school, so you might have learned of it. This is probably the most important concept in Stats 101, which is called the central limit theorem. So that's what we're going to go and learn about, which is, I don't think it's very difficult. It could get complicated if you try to like think about it too much, but it probably will make sense, and we'll do some activities so it makes sense. But that's what we're going for. But let's start with a visualization activity. Okay, so what I did, guys, go to Blackboard. I'm so proud of myself that I did this. So it's like not a big deal. In content, under class recordings, now I have a separate folder that says New York Times visualizations. So I'm just going to keep all of those there because it actually makes more sense to keep it there as opposed to under a certain topic, because the visualizations don't necessarily relate to the topic specifically. Okay, so if you go in there, the fourth one that is there is consumption during the pandemic. Okay, so go ahead and click on that. And we'll see what's going on. So this is a very relatively recent article from the New York Times. And, oh, that's the wrong link. Does that go to what effect does what we eat? Does it go to that link, guys?
Yeah.
Oh
I
my
think we
God.
did it already.
No, we did do that. That's not what I meant to put there. Give me 1 second. Oh my God, what happened? Pandemic consumption, here it is. Yes, here we go. So we're gonna look at consumer spending during the pandemic. Without looking at it, what do you guys think happened? Maybe even from your own experience, what happened in terms, what changed, let's say compared, so let's start with March-ish, March through something like September. Compared to March through September last year, has there been any changes in your spending, guys? And if so, in what way?
Wait, Professor,
Yeah.
do we stay in the one where it's like the slide?
I'll give you a new link. Sorry, that link was not supposed to be like there. Copy link. Okay, so I'm gonna put it in the chat right here, and then I'm gonna update the Blackboard link as well, so you can get it from. But you should be able to go into this one. So slide 2 is a little bit pixelated. So slide 3 is going to kind of give you a little bit better. And also in the comment section, I give you the original link to that PNG. So you can click on it and have a better accurate or like a more zoomed in version of it. But apparently this is what's been happening in August retail sales from all these different industries. So take a look. So what's going on, guys? Let's take a look together. What's going on? Anything you notice?
I think non-store retailers increase a lot.
What store retailers? What happened?
Non-store, like not a physical real store.
Okay, like online stores is what you mean?
Yeah.
Nice. Yes. So that definitely makes sense that it happened. Oh, I see. Non-store retailers, like at the top. Yeah. So definitely all these online places are seeing a hike for sure, which makes sense. What else do you guys notice? And do these kind of like make sense? Does it align with what your purchases were like in the past few months compared to like, let's say 2019? Or is it grossly different? What's going on?
For me, I think it's really similar to like what my life has been like for these past couple of months.
Least similar.
No, it's very similar. Like
Oh.
compared to me, like going into a store and doing shopping, I've been spending all my money online.
Yeah. Are you also so which is not surprising, I guess. Are you guys also, in terms of if you bought any clothes or something, is it mostly like sporting gears and comfortable clothes and yoga pants and all these things? Apparently, for in terms of clothing retail, this has been a huge spike. You guys agree?
Yeah, honestly, it's nobody's really wearing jeans while they're lounging in their couch.
Yes, indeed. So apparently that's been going up. I remember during the pandemic, I was not in this state, but I was in Connecticut, and we went to a Dick's a store, and this Connecticut opened up a lot sooner than New York did, and we wanted to get some biking gear, and literally the entire biking section was empty. That whole side of the store was empty. Everything was sold out except maybe like 3 bikes that were meant for infants, basically, that nobody can actually use except infants. Ashley ordered more t-shirts. I'm assuming like maybe comfortable t-shirts. Lululemon still on good pace during the pandemic. Is that right? Very good. What else do we see? So look about the negative ones, guys, on the bottom. What's interesting about that? That's weird. I don't think electronics would have gone down. Well, I might be thinking of very specific. Yeah.
Keep reading articles in Apple and Google, and apparently they kept delaying the release of the iPhone 12 because they didn't really think consumers would go out and purchase it in the middle of this pandemic. Everybody was more worried on food. So they only released it until now, they were supposed to be released at the beginning of summer, but they delayed it all the way until October.
Oh, and that, I mean, I guess you can never know because you can't compare to the time you did release it in September because they didn't do that. But I wonder if that did help them. I thought, I don't know why you would do this in the pandemic, but even before that, I don't understand. But apparently there were lines in front of these Apple stores, even before the release, because they just wanted to look at it. I'm like, really?
And what's crazy is because I had to go to the Apple store last week to get my phone fixed, and the guy told me that they're actually not giving out accessories with the phones anymore. So like, if you buy a new phone, you're not getting a new charger, you're not getting headphones, so you have to keep all your accessories because they're trying to be clean by like 2030, and like all the third companies that sell like Apple accessories is contributing to like the pollution in the ocean. So they feel like if they stop supplying accessories, that it will decrease.
I mean, it is true. You kind of have to be more responsible.
Is it cheaper then? You have to get a charger.
No, it's expensive. I lost my AirPod case and it's so expensive. It's like $60 for a replacement. So I had to go on eBay.
That is so. So
I actually don't think it makes sense
like
because
my
like
responsibility.
third-party accessories, they mess up your phone in a sense. Like if you get a charger from Amazon, it could potentially damage the system in your phone. So you would just have to go back to Apple and replace it. So it's like regardless, they're still getting our money in a way.
Guys, you need to boycott Apple. That's horrendous. That's one of the worst things I've heard since they got rid of the headphone jack.
You can try to boycott them, but when I went to go buy my MacBook and I went to go get an iPhone, there were 2 lines and it didn't look like 2 lines. It just looked like it was filling up an entire floor of the mall. That's how long, and everybody was standing so close to each other.
Ooh. Oh my God, that is true. That Apple like just keeps coming up with new horrendous policies. That just like, I'm like, oh my God. It's like they can do anything to you and you're still gonna go buy their stuff. Trust me.
I mean, we kind of are.
My God, that's terrible. Who doesn't give you a charger?
Yeah, they don't. They don't give them to you anymore.
Doesn't matter. I don't like use Apple products. It's horrendous anyways. Except my laptop, but FIT gave that to me, so. And there's some of the things that I do in my programming that the Windows just like is a little bit complicated. That's terrible. Why would they not give you a charger? That's horrendous. You guys should all abandon Apple. Oh my God. I'm going Chromebook next time. But Chromebook is also really hard to get on the FIT network. It's just like, maybe I will think about Windows. I'll just like put a Linux system on it. It's not deal with it.
I mean, Apple did get a brand new like USB port. So now like the brand new port can be used in both Android and Apple products. So like my MacBook charger can be used on my Google Pixel. So it's like it's not specifically tailored to Apple only.
Oh, that's surprising. Can't believe Apple did that.
Wait, Professor, I don't know if I'm reading the graph right, but so I'm looking at the graph, right? And then so red going towards the right means that the sales increased.
Correct. Right? That's how I'm reading it, guys. I think yeah. Are you guys reading it that way too? That's how I'm reading it. Yep. So
and then yellow.
Yellow and orange, the only difference is that yellow is comparing to the previous year and the orange is only comparing to the previous month.
Okay.
Yeah,
and then
right.
yellow towards the left means that the sales decreased, right?
Correct. So you see those negative percentages next to those ones on the bottom, those are negative.
Okay, yeah, just wanted to make sure. All right, thank you.
Yeah. So the reason why that's how we started talking about Apple, because it's electronics. Because I mean, those are not electronics, but gaming companies have been soaring. They're just like selling like crazy. But I thought because of that, like consoles and these different things related, like equipment, basically electronics related to gaming were increasing in sales too. But I mean, electronics includes almost everything, right? That includes TVs and everything. So maybe overall it decreased a little bit. Appliances, maybe those are kitchen appliances too. Although I recently went to Home Depot. My gosh, guys, it was packed because everybody's doing home improvement, which is the reason why I was there as well. Yeah, it was packed. Everybody's like, so building materials, garden, you see that how that increased. And then furniture and furnishings that increased. I wonder if that's kind of like the Home Depot and Lowe's area. So those are increasing. Everybody's trying to make their surroundings more pleasant, which makes sense.
Professor?
Yep.
So you're saying that electronics did increase in the previous month compared to last year?
So in the specific electronics I'm thinking, I know that a lot of gaming companies and gaming consoles, they're doing pretty well. So gaming is software, so obviously that's not electronics. But I know some gaming consoles are doing pretty well because people are at home more and they're playing more games. But electronics probably includes everything, as I was saying, like toasters, TVs, like washers, dryers, right? It includes everything. So I think that's why it's a negative thing, because maybe people are ordering less of those things because they don't want people to be visiting or something. I don't know. It's a pretty broad category.
Wait, I'm just asking to make sure I'm reading the graph correctly. So for the previous month, it did increase, and last.
Correct.
Okay.
Yeah, but not for the previous year, it looks like.
Yeah, okay.
Yeah. Yep. All right, very good. So yeah, you guys know the drill. You guys are already doing it. Claim a thing, claim a slide, and answer the questions. See if we get any catchy titles. Main idea. The COVID commerce. You guys are so good at alliteration. Good job, Zach. I like. Home improvement mania, Delia says. Sienna's like, say goodbye to in-store shopping. Yeah, what's gonna happen, guys? I mean, you guys are in fashion. All these retail stores are just closing down.
Yeah, that's pretty much what it is. Like my job that I was working at, it closed, and like retail sucks right now.
Yeah. I mean, it's hard to say what's gonna happen moving forward, right? Like, is it just gonna go back to where it was? Or I know a lot of what's it called? Those big bank and investment companies that used to dominate like the downtown retail spaces. They're definitely reconsidering their office space. Like they know they don't have to rent as much. and giving their employees the option to work from home. Even when the vaccine comes out, they're gonna like think about those options, so they don't have to rent out office space, like as much office space, right there. Well, from an article, so CEOs of like Morgan Stanley, and they've been saying something like that as a permanent policy they might have. So, you know, things are changing.
Some companies are actually pretty innovative. Like I recently went to this Mac store and it used to be like just a regular Mac cosmetic store. And now when I go in there, they changed the entire design. So now you don't even have to try on anything. They have virtual screens all over the store where you just click on the product you want and it'll like virtually try it on for you.
Yeah. So those are called virtual mirrors, and a lot of fashion places are trying that out so that, you know, the person, I think there's a name like that, a name for, anyways, an associate in the store doesn't have to like bring you this and go back and bring you this and like do that, but you can kind of try it out. So those are happening. Those have been happening even pre-pandemic though. It's just like some companies have not done it yet. So those are happening. Yeah, I mean, it is going to be a lot more contactless things. Yeah, I don't know. So things are changing. Maybe, I mean, oh, you guys are not in my machine learning course, so you guys don't know. But, you know, some of the things that I talk about in class and people already know of, Sephora has this app where you can try on makeup, right? I think it was Modi, what was it called? Modi something, and you can try on a hair dye color. So you can put on you can put red color on my hair and see how that would look like. Warby Parker does this thing where on your face, you can try on the different glasses before you order them, right? These are all AI stuff. So these things that have been happening. I mean, pre-pandemic, it's just, we don't like see it heavily around. We didn't see it heavily around, but maybe that will be kind of like the main thing. Lululemon came out with a workout mirror, and the SoulCycle bike can now be bought or rented. Peloton is also becoming popular at home. Yeah, Peloton is definitely doing something. So is that, I feel like I've been seeing this ad where it's like, it's not just a mirror, and it's like, basically it's a screencast, and like people, like what you see on YouTube, you see it on the mirror, and then you also see yourself. That's what that is. Is that the same thing?
Yeah, I think it is. It like lights up with whatever the workout is.
No, let's see. They make it sound like it is the like cutting edge technology. I'm like, that's just a screencast. I don't know what's the big deal about it. It's Wii Fit, but like bougie. Is it? What's Wii Fit? Isn't Wii just like I guess I only know the games, and then with the games you could, is that the one where you can put that thing around your like thighs or something, and like as you move up and down, like basically you're doing a workout? I think that's what it was, right?
Yeah, well, this was like back in the like mid to like late, like 2007 to like 2010. Like there's like a little thing that you could stand on, and then like you had like Wii bowling and like Wii like tennis.
Oh, no, I'm thinking about that. What's that thing? The kind of like the most recent one. It was like kind of like a little bit before the pandemic. In 2019, it came out. Maybe it wasn't Wii. That's why. There's this thing where you can put it around your thighs or like arm, and like as you move, like you have to move it for the game character to move or something like that. What's the name?
I think that's like a new Wii.
It's like an exergame thing. Exergame. It doesn't matter. Anyways, that exists. Okay. Well, anyways, all these things are happening. Changes are happening. Changes could be good. We don't know. We'll see what happens. But I do like. I don't know if it's actually true, but I know at least in the beginning of the pandemic, a lot of people were like, "Okay, I'm going to take this opportunity to get fit." I don't know if that actually happened for the majority. I was thinking the same thing, and the only thing I did was drink more and eat more and gain weight. So, but it's like, you know, at least the mindset, people were like, let's take this opportunity to improve yourself, right? I don't know if that happened. Did that happen for anybody? That might have been Nintendo. You're right, Marco. I forget which one it was. Ashley's like, no. Oh my God, aren't you like so kind of almost angry at the people who got more fit during the pandemic? My like gym trainer, he just got so freaking buff. I was like, oh my God. It's like lifting hundreds of 100-pound, like 200-pound like dumbbells and stuff. Is that possible? You should see my gym trainer. It's like pretty much an NFL player, except he's not. Oh God. It's like, how are you more fit? How is this possible? It's because his gym was closed and he had the whole gym to himself and nothing else to do. So he just kept working out. I was like, oh my God. So motivated. All right, guys. Great. Finish it up. I see some of you guys have your name on the slide, but I don't see any answers. Okay, so try to answer these questions. I'll give you till the end of the day to do this. Okay, so I'll check in later. But this is, this is part of your in-class participation. So I want to see some answers here. Okay. All right. Okay, so now let's actually move on to our new topic. The most important topic that you will learn probably this semester, the central limit theorem. All right. Marco's trying to be like him. You don't even know him. I used a Bowflex for a short time, but I lost all motivation. What's a Bowflex?
I think it was like a workout program that was like really popular at a certain time. I think it was like similar to like, have you ever heard of like Tybo or like
Oh yeah. Of course. Yeah.
I think it was like a workout program that like is available to you
Tybo.
like buy or something.
Yeah, I see. It's a workout machine. All right. We gotta have all these machines and all these algorithms helping us just to motivate ourselves to move around, huh? All right. I'm gonna share my screen. We're gonna start with the central limit theorem. So we're moving on to new topics, guys. So in terms of Blackboard, it's gonna be the next folder under 4 normal distributions. And inside there's the links for the video I'm about to show you, okay? But you don't have to worry about where to find it. I'm gonna share my screen for now, okay? So central limit theorem is what we're going for. Very, very important, guys, okay? Very, very important. This is like such an important topic. All right, here we go. If I can get my computer to kind of actually work. All right, here we go.
Central limit theorem. And what it tells us is we can start off with any distribution that has a well-defined mean and variance, and if it has a well-defined variance, it has a well-defined standard deviation. And it could be a continuous distribution or a discrete one. I'll draw a discrete one just because it's easier to imagine, at least for the purposes of this video. So let's say I have a discrete probability distribution function, and I want to be very careful not to make it look anything close to a normal distribution because I want to show you the power of the central limit theorem. So let's say I have a distribution. Let's say it can take on values 1 through 6. 1, 2, 3, 4, 5, 6. It's some kind of crazy dice that's very likely to get a 1. Let's say it's impossible. Let me make that a straight line. You're very high likelihood of getting a 1. Let's say it's impossible to get a 2. Let's say it's an okay likelihood of getting a 3 or a 4. Let's say it's impossible to get a 5. And let's say it's very likely to get a 6 like that. So that's my probability distribution function. If I were to draw a mean, this is symmetric, so maybe the mean would be something like that. The mean would be halfway, so that would be my mean right there. The standard deviation, maybe it'd be that far and that far above and below the mean. But that's my discrete probability distribution function. Now what I'm going to do here, instead of just taking samples of this random variable that's described by this probability distribution function, I'm going to take samples of it, but I'm going to average the samples and then look at those samples and see the frequency of the averages that I get. And when I say average, I mean the mean. So let's say, let me define something. Let's say my sample size, and I could put any number here, but let's say first off, we try a sample size of n is equal to 4. And what that means is I'm going to take 4 samples from this. So let's say the first time I take 4 samples, so my sample size is 4. Let's say I get a 1, let's say I get another 1, and let's say I get a 3, and I get a 6. So that right there is my first sample of sample size 4. And I know the terminology can get confusing because this is a sample that's made up of 4 samples. But when we talk about the sample mean and the sampling distribution of the sample mean, which we're going to talk more and more about over the next few videos, normally the sample refers to the set of samples from your distribution, and the sample size tells you how many you actually took from your distribution. But the terminology can be very confusing because you could easily view one of these as a sample. But we're taking 4 samples from here. We have a sample size of 4. And what I'm going to do is I'm going to average them. So let's say the mean, I want to be very careful when I say average, the mean of this first sample of size 4 is what? 1 plus 1 is 2, 2 plus 3 is 5, 5 plus 6 is 11, 11 divided by 4 is what? 2.75. 2.75. That is my first sample mean for my first sample of size 4. Let me do another one. My second sample of size 4, let's say that I get a 3, 4, let's say I get another 3, and let's say I get a 1. I just didn't happen to get a 6 that time. And notice, I can't get a 2 or a 5. It's impossible for this distribution. The chance of getting a 2 or 5 is 0, so I can't have any 2s or 5s over here. So for the second sample of sample size 4, my sample mean for my second sample mean is going to be 3 plus 4 is 7, 7 plus 3 is 10, plus 1 is 11, 11 divided by 4 once again is 2.75. Let me do one more because I really want to make it clear what we're doing here. So I do one more. Actually, we're going to do a gazillion more, but let me just do one more in detail. So let's say my third sample of sample size 4, so I'm going to literally take 4 samples. So my sample is made up of 4 samples from this original crazy distribution. Let's say I get a 1, a 1, and a 6, and a 6. And so my third sample mean is going to be 1 plus 1 is 2, 2 plus 6 is 8, 8 plus 6 is 14, 14 divided by 4, 14 divided by 4 is what? 3.5, 3.5. And as I find each of these sample means, so for each of my samples of sample size 4, I figure out a mean. And as I do each of them, I'm going to plot it on a frequency distribution. And this is all going to amaze you in a few seconds. So I plot this all on a frequency distribution. So I say, okay, on my first sample mean was 2.75. So I'm plotting the actual frequency of the sample means I get for each sample. So 2.75, I got it one time. So I'll put a little plot there. So that's from that one right there. And I got the next time, I also got a 2.75. That's a 2.75 there. So I got twice. So I'll plot the frequency right there. Then I got a 3.5. So all the possible values, I could have a 3, I could have a 3.25, I could have a 3.5. So then I had the 3.5, so I'll plot it right there. And what I'm going to do is I'm going to keep taking these samples. Maybe I'll take 10,000 of them. So I'm going to keep taking these samples. So I go all the way to 10,000. I just do a bunch of these. And what's going to look like over time is each of these, I'm going to make it a dot because I'm going to have to zoom out. So if I look at it like this, over time, still it's all the values that it might be able to take on. 2.75 might be here. So this first dot is going to be, this one right here is going to be right there. And that second one is going to be right there. And that one at 3.5 is going to look right there. But I'm going to do it 10,000 times because I'm going to have 10,000 dots. And let's say as I do it, I'm going to just keep plotting them. I'm just going to keep plotting the frequencies. I'm just going to keep plotting them over and over and over again. And what you're going to see is, as I take many, many samples of size 4, I'm going to have something that's going to start kind of approximating a normal distribution. So each of these dots represent an incidence of a sample mean. So as I keep adding on this column right here, that means I kept getting the sample mean 2.75. So over time, I'm going to have something that's starting to approximate a normal distribution. And that is the neat thing about the central limit theorem. So the central limit, and this was the case for, so in orange, that's the case for n is equal to 4. This was for sample size of 4. Now, if I did the same thing with a sample size of maybe 20. So in this case, instead of just taking 4 samples from my original crazy distribution, every sample, I take 20 instances of my random variable, and I average those 20, and then I plot the sample mean on here. So in that case, I'm going to have a distribution that looks like this. And we'll discuss this in more videos. But it turns out if I were to plot the sample, 10,000 of the sample means here, I'm going to have something that, two things. It's going to even more closely approximate a normal distribution, and we're going to see in future videos it's actually going to have a smaller. Well, let me be clear. It's going to have a small. It's going to have the same mean. So if that's the mean, this is going to have the same mean. But it's going to have a smaller standard deviation. So I want to. Well, I should plot these from the bottom because you kind of stack it. One you get one, then another instance, and another instance. But this is going to more and more approach a normal distribution. So the reality is, and this is what's super cool about the central limit theorem. As your sample size becomes larger, or you can even say as it approaches infinity, but you really don't have to get that close to infinity to really get close to a normal distribution. Even if you have a sample size of 10 or 20, you're already getting very close to a normal distribution. In fact, about as good an approximation as we see in our everyday life. What's cool is we can start with some crazy distribution. Right? This has nothing to do with a normal distribution. But if we have a sample size, this was n equals 4, but if we have a sample size of n equals 10 or n equals 100, and we were to take 100 of these instead of 4 here and average them and then plot that average, the frequency of it, then we do take 100 again, average them, take the mean, plot that again. And if we were to do that a bunch of times, in fact, if we were to do that an infinite time, we would find that especially if we had an infinite sample size, we would find a perfect normal distribution. That's the crazy thing. And it doesn't apply just to taking the sample mean. Here we took the sample mean every time, but you could have also taken the sample sum. The central limit theorem would have still applied. But that's what's so super useful about it. Because in life, there's all sorts of processes out there, proteins bumping into each other, people doing crazy things, humans interacting in weird ways, and you don't know the probability distribution functions for any of those things. But what the central limit theorem tells us is that if we add a bunch of those actions together, assuming that they all have the same distribution, or if we were to take the mean of all of those actions together, and if we were to plot the frequency of those means, we do get a normal distribution. And that's frankly why the normal distribution shows up so much in statistics, and why frankly it's a very good approximation for the sum or the means of a lot of processes. Normal distribution. What I'm going to show you in the next video is I'm actually show you that this is a reality, that as you increase your sample size, as you increase your n, and as you take a lot of sample means, you're going to have a frequency plot that looks very, very close to a normal distribution.
All right, so how was that? So I want to make sure, I don't know if it was emphasized enough, but this is a very, very important concept in statistics. And you guys might have even asked, oh my God, we've been like doing the normal distribution, standard normal distribution, like so much of it. One of the reasons why that is such a big topic, it's because of this central limit theorem, right? There's a lot of, as he said, a lot of processes out there, right? Proteins bumping into each other, people interacting with it in weird ways. We just looked at visualizations about like increases in sales, decreases in sales, like all these kind of phenomena occur, and how those distributions are, all of them are going to be different. The original distribution is going to be different. However, if we take a sample of that and average it out, right? So therefore the mean, and then we plot that in a new graph about the frequency, about how many of those means appear, you will end up with a normal distribution. This is true for pretty much everything that you will deal in real life. There's a few exceptions, and that's like beyond kind of what we're going to learn today or this class, but everything can be plotted as a normal distribution when you take a mean of the samples of a crazy probability, like not a normal distribution. It starts out with something crazy where a peak is here, maybe it's right skewed or it's left skewed, like the one Khan Academy was showing, like there's two peaks at the edge, like so it's bimodal. Whatever the original distribution is, if you take a sample from that same distribution and average each of those samples and then plot those averages on a frequency, basically the frequency of that, you will end up with a normal distribution. Does that, I don't know how to emphasize it more. It's very, very important. I mean, isn't that kind of cool that that happens? Maybe not. Okay, so that's the core concept we're gonna learn. Let's go with the next video that it's in connection to this one that I wanna make sure that you guys see. And then in that, he's gonna show us a little activity that we're gonna also do as well. Okay, all right, here we go. Just share this again. Put any questions in the chat. If you don't understand it yet, that's okay. Okay, this is gonna be a little bit of a slow process. It takes a little bit to maybe understand it, but once you do, it will make a lot of sense. Okay, all right, here we go.
In the last video, we learned about what is quite possibly the most profound idea in statistics, and that's the central limit theorem. And the reason why it's so neat is we can start with any distribution that has a well-defined mean and variance. Actually, I wrote the standard deviation here in the last video. That should be the mean, and let's say it has some variance. I could write it like that, or I could write the standard deviation there. But as long as it has a well-defined mean and standard deviation, I don't care what the distribution looks like. What I can do is take samples in the last video of, say, size 4. So in this, that means I take literally 4 instances of this random variable. This is one example. I take their mean, and I consider this the sample mean for my first trial, or you could almost say for my first sample. I know it's very confusing because you can consider that a sample, the set to be a sample, or you could consider each member of the set as a sample. So that can be a little bit confusing there. But I have this first sample mean, and then I keep doing that over and over. In my second sample, my sample size is 4. I got 4 instances of this random variable. I average them. I have another sample mean. And the cool thing about the central limit theorem is as I keep plotting the frequency distribution of my sample means, it starts to approach something that approximates the normal distribution. And it's going to do a better job of approximating that normal distribution as n gets larger. And just so we have a little terminology on our belt, this frequency distribution right here that I've plotted out, or here, or up here, that I started plotting out, that is called, and it's kind of confusing because we use the word sample so much, that is called the sampling distribution of the sample mean. And let's dissect this a little bit just so that this long description of this distribution starts to make a little bit of sense. When we say it's the sampling distribution, that's telling us that it's being derived from, it's the distribution of some statistic, which in this case happens to be the sample mean, and we're deriving it from samples of an original distribution. So each of these, so this is my first sample. My sample size is 4. I'm using the statistic, the mean. I actually could have done it with other things. I could have done the mode or the range or other statistics. But the sampling distribution of the sample mean is the most common one. It's probably, in my mind, the best place to start learning about the central limit theorem and even, frankly, sampling distribution. So that's what it's called. And just as a little bit of background, and I'll prove this to you experimentally, not mathematically, but I think the experimental is on some levels more satisfying with statistics, that this will have the same mean. This will have the same mean as your original distribution. Right here. So it has the same mean, but we'll see in the next video that this is actually it's going to start approximating a normal distribution, even though my original distribution that this is kind of generated from is completely non-normal. So let's do that with this app right here. And just to give proper credit where credit is due, this is, I think it was developed at Rice University. This is from online statbook.com. This is their app, which I think is a really neat app because it really helps you to visualize what a sampling distribution of the sample mean is. So I can literally create my own custom distribution here. So let me make something kind of crazy. So that you can do this in theory with a discrete or a continuous probability density function. But what they have here, we can take on one of 32 values, and I'm just going to set the different probabilities of getting any of those 32 values. So clearly this right here is not a normal distribution. It looks a little bit bimodal, but it doesn't have long tails. What I want to do is first just use the simulation to understand or to better understand what the sampling distribution is all about. So what I'm going to do is I'm going to take, let's start with 5 at a time. So my sample size is going to be 5. And so when I click animated, what it's going to do is going to take 5 samples from this probability distribution function. It's going to take 5 samples, and you're going to see them when I click animated. It's going to average them and plot the average down here. And then I'm going to click it again. It's going to do it again. So there you go. Got 5 samples from there. It averaged them, and it hit there. Oh, what did I just do? I clicked. Oh, I wanted to clear that. Let me make this bottom one none. So let me do that over again. So I'm gonna take 5 at a time. So I took 5 samples from up here, and then it took its mean and plotted the mean there. Let me do it again. 5 samples from this probability distribution function, plotted it right there. I could keep doing it. It'll take some time, but as you can see, I plotted it right there. Now, I could do this 1,000 times. It's going to take forever. Let's say I just wanted to do it 1,000 times. So it's this program, just to be clear, it's actually generating the random numbers. This isn't like a rigged program. It's actually going to generate the random numbers according to this probability distribution function. It's going to take 5 at a time, find their means, and then plot the mean. So if I click 10,000, it's going to do that 10,000 times. So it's going to take 5 numbers from here 10,000 times and find their means 10,000 times and then plot the 10,000 means here. So let's do that. So there you go. Notice it's already looking a lot like a normal distribution. And like I said, the original mean of my crazy distribution here was 14.45. And the mean of, after doing 10,000 samples or 10,000 trials, my mean here is 14.42. So I'm already getting pretty close to the mean there. My standard deviation, you might notice, is less than that. We'll talk about that in a future video. And the skew and kurtosis, these are things that help us measure how normal a distribution is. And I've talked a little bit about it in the past. And let me actually just diverge a little bit and just so it's interesting. And they're fairly straightforward concepts. Skew literally tells.
So I won't go into that part. It's helpful, but for the purpose of this class, you don't really need to know that. So let's go ahead and try that simulation out ourselves, okay? And that might be a better visual, and the interactiveness of this might help you understand this better. I am going to assume these 2 videos might have not been enough for you guys to understand this concept, but this is a soft introduction. Don't worry about it. We're going to spend a few classes on this, but it's a very, very important concept, okay? So what I want you guys to do now is go to Blackboard and go to Content. And you will notice, finally, we are moving to the next topic. So that's a brand new folder. And it says Sampling Distribution of Means. Remember, Khan Academy was, he was talking about the sampling distribution of sample means. And it was kind of like quite a bit of a loaded sentence. So that's our new topic, basically. And if you click inside that, there's going to be the readings, the New York Times things, which I'll get rid of soon. And if you scroll down, the very first video we saw is there. That's titled Central Limit Theorem. And the one we were just looking at was a sampling distribution of the sampling mean, which we were just looking at, and I kind of stopped. Right underneath that, you're going to see Rice Uni Online Stat Interactive Book. So that's the Rice University Online Stat Interactive Book that he was giving credit for, and he was showing you. Go ahead and click on that and open it up. Everybody go ahead and do this. And then if you see on the left side, you're going to see a little button that says begin. Do you guys see that? Click on that and you'll see a similar yellow background page like he was showing you. If you did get there, chat me and say that you are there. If you're confused where to go, ask. Okay, good. A lot of you guys are there. Awesome, awesome. Okay, so this is what we're gonna do. And I can share my screen to show you guys. So you guys are gonna do what basically Khan was doing, and you guys are do your own thing. So at the very top, you guys are gonna see, let me zoom in a little bit for you guys. Is it gonna work for me? Come on, zoom in, zoom in, zoom in. Okay, so I'm a little bit more, maybe a little bit zoom. Okay, so we have like a distribution here, right? And it could be of anything, right? Go ahead and click on all these things and create something like super crazy. something that basically is not a normal distribution, right? Meaning that it's not a bell curve, right? And you can create whatever you want. You can see that you will be able to drag down these things or drag it up if you want, as long as your screen allows. It's gonna give you all kinds of stuff, right? So try to create something that is as non-normal as you can think of. And when I say non-normal in this context, meaning a non-normal distribution. So anything that really does not look like a normal distribution, try to create something like that, right? I'm gonna have all these like weird peaks everywhere, right? This is definitely very, very far from a normal distribution, right? So maybe do something like that. Whatever you want, okay? And so let's pretend whatever the context was, this is our distribution. This is what we have. And based on all of this, it's from something from 0 to 32, okay? Let's just pretend, I don't know, like let's say these are like the daily, I don't know, hot dog sales at this corner, like little cart down the street from FIT or something like that. I don't know, something, it could be anything, right? So we have this, and nicely, automatically, it's going to calculate the mean for you. So the mean is somewhere around 16.8. The median is 16. So the mean and median are quite close to each other, kind of like our midterm. And then we have a pretty high standard deviation of 7.91, right? Because it's just all over the place. And don't worry about the skew and kurtosis, right? We're not going to cover that in this class. Okay, so we have something that's very, very non-normal. And what we're going to do is we're going to do what he just did. He did this kind of in the first video by actually calculating it by hand. And then he did it in this simulator, right? We're going to do the same thing. So what we're going to do is, let's in here, you can choose an n of whatever you want. But let's start something like n of 5. Meaning that I'm going to take out of this distribution, I'm going to randomly select 5 x values. Okay? I'm going to select 5 of them. And then what I'm going to do with those 5 things is going to be, I'm going to average it, right? I'm going to add them together and divide it by 5, okay? And you can do that. You can do that if you do animate it, it's going to do that. So it's just going to select 1, 2, 3, 4, 5 of those. That's like 1 data value each. When it dropped, that was 1 data value. That's 5 of them. And then automatically the system took the average of it. So added those 5 and divided it by 5, right? So something like, I don't really know what this is, but let's see, maybe that's 16, 18, whatever, 20, whatever those numbers are, were added together and divided by 5. And that average number is plotted right here. That's 1 point, 1 plot right there of the frequency, okay? And then you can do it again. And then it's going to choose another 5 random numbers, and then it's going to plot that frequency on top of the first one. And then you can do it again. It's the 3rd time it's doing it. And then you can do it again, the 4th time it's doing it. And it's going to continue to do it as long as you keep pressing the animated button, right? With an n of 5, always choosing 5 from this original distribution. And what you can see is that every time the average is taken and it's plotted on this frequency distribution, or distribution of means as we're calling it, it's going to eventually, with enough trials, it is eventually going to become a normal distribution. But since this is going to take a long time, we're going to go ahead and click on the 10,000 button, because I want you to, what we were doing one time, I want this system to do this 10,000 times immediately. So we're going to do that, and then it plotted all of it, and it is almost like a perfect normal distribution. I say almost because you kind of have to get even a higher number to get to like a perfect normal distribution. But you can see as more trials you do, so the original distribution was 16.8, the mean, and the mean of this one when you did 10,000 trials. Actually, I did 10,011 because originally I was clicking it 11 times apparently, and then I added another 10,000. So when I did it 10,011 times, my mean is about 16.81. So it's almost approaching the same thing, right? Let's go ahead and do 100,000. I'm going to do that. And now it's 110,011 times, and the mean is now 16.79. So compared to 16.81, it's still like a little bit away from the original mean, but it's really getting close, okay? And so this is an illustration of the central limit theorem, right? It's if you take some random, non-normal, weird distribution and take a sample of them and average that and then plot that average by frequency, you will end up getting a normal distribution. That is the core of central limit theorem. So go ahead, just like I did, create something really crazy. And
I have a question.
Yes.
So on what you just did, was the skewed 0.05 skewed to the left?
0.05.
Because when you did it, you said you did it 11 times and it wasn't perfect because it had a skew. So was the skew to the left or to the right? I think, is it to the left, right?
I mean, when you do something 11 times, it's hard to say something skewed to the left or right. That's just not enough samples to kind of come to that conclusion just yet. So I would say it wasn't skewed to anything because it was just not enough to kind of like draw something around it and be like, oh, it's skewed to the left or the right.
So you're saying it wasn't skewed, but it also wasn't perfect.
Correct. It was nothing near perfect. And it was just kind of like plotting a few things, and it's a little too few samples to kind of draw any conclusions like that.
All right, thank you.
Yeah. All right, so go ahead and create an original distribution that's super crazy. Maybe it's all the same height, it's uniform, it's all low, or it's just like going all crazy, whatever you want, whatever creative side tells you to do that. And then this time maybe take a n of some other number. The higher the number, the better. So maybe you take 10 samples each time, or 15 samples, or 20 samples each time, and then try the animated thing one by one, and then try it 5 times, and try it 10,000 times, and see what you get. And then delete, clear all of it up, and then try another crazy non-normal distribution and do the same thing. And see if you actually end up with a normal distribution in the end. Go ahead and do a few samples of those. And if yeah, go ahead.
If the sample size, like, would the sample size change or does it have to stay the same?
The sample size can change. So I was showing you that the n of 5 is what we started with, but you don't have to only pick 5 random things. You can pick 10 random things, or you can pick 20 random things and continue to go. So you can choose whatever sample size you want. In terms of a question, when you answer a question, the sample size is going to be given to you.
Okay, so like, but essentially, like, if, like, let's say like you did like 100,000 reps of like sample like size of 5, but then you're like, okay, so like for the next like 300,000, I'll do a sample size of like 10. It won't like change the graph in any way.
Well, it will be kind of a little bit different, but in the end, based on the central limit theorem, you'll still end up with a normal distribution or something very close to a perfect normal distribution.
Okay, but it'll still be like the same like mean, essentially.
Correct. It will approach the same mean for both instances. So if you are asking, so you shouldn't plot, if you started with n of 5, for example, and you plotted so-and-so 10,000 times, you shouldn't choose a different sample mean and do 10,000 times and plot that over that. Those two should be separate. But when you do it separately, n of 5, 10,000 times, and n of 20, 10,000 times, both of those results will be very similar, like a normal distribution, and the mean should come pretty damn close to each other.
Okay.
So if the videos were not very easy to understand, then try to focus on the simulation and just take it, what's the expression? Take it at face value, right? Don't try to think too much in a complicated way, but just look and click and accept what you see. Just take it as at face value, that this is what happens with data in the world. This is what happens, you know, from all the gazillion times statisticians have done and collected and simulated this and done this by hand or using a computer to simulate this, this does indeed happen. And this is related to all the things that happen in the real world, which is why normal distribution is covered so much in statistics. Any kind of more abstract questions or conceptual questions you might have. We actually are running out of time. So after we finish our simulations, I'm going to end the class, but I do want you to kind of start thinking about what this means. Not too like crazy, like don't try to go so philosophical. In some ways, you kind of just have to accept that this is what happens. You know, it's kind of like when I was a little kid, this took me so long. When I first learned about like multiplying fractions, to me, for the longest time, it made no sense. I was like, you taught me that when you multiply, things get bigger. And it's not getting bigger. It's not getting bigger. And I like just in my mind, I was refusing to understand it. So if you do times 1/2, I was like, why isn't the number getting bigger, but it's getting smaller? And it just took me a very long time to kind of accept it. I mean, I understood it too, but it took me a long time to accept it. I don't know why that was so confusing, but it was at the time. And some, I think, math topics are just kind of like that. It takes a while. In one way or another, you just kind of have to accept it. You know how we're all like, we accept who you are the way you are? Same kind of thing. These are things that do happen in the real world if you do it mathematically. And this is a phenomenon that happens, and it's an important theory. It happens to be because it's applied everywhere in the real world. Okay, so you kind of have to let it simmer and marinate, and like kind of have to accept it as well. Creating some crazy distributions, guys. Because we only dealt with kind of very clean distributions so far, right? It's either right skewed or left skewed, or everything's like uniform. Uniform is when all the kind of heights are the same, like a plateau. Sometimes you'll see like two humps, and we did say bimodal, but I didn't really cover that specifically in class, but like at one point or another, you might have heard of it. So we've dealt with those, but like the ones I was creating with like ups and downs and craziness, you know, we haven't really seen anything like that. So create something like that and see what at the end, what you get when you take the mean of the samples and plot that. And obviously we will talk about this more next class, and it'll probably trickle into the following week as well, because it's such an important concept. Okay, so I'm gonna let you guys go. As you know, I always kind of just run through and try to let you guys out a little early without a break in between. So I'm gonna let you guys go. Let this kind of marinate, just think about it. There's no homework regarding this new topic, but remember, you do have to finish problem set 4 and problem set 5. Problem set 5 should only have 5 questions or something, so it's really a short one. But remember to finish those 2 by Friday. I think the deadline is 11 a.m. or 12 p.m. or something like that. Basically, kind of before class on Friday. Okay, are we good? All right, I'll see you guys Friday.
Professor.
Thank you, Professor.
Thank you.
Thank you.
Professor, I have a question.
Yes, please.
Right, we also had to do like module 4 or something like that.
Oh, the spreadsheet, right?
I didn't see anywhere to submit it, so I just shared it.
Yeah, that's fine. That's fine. I will create something and then we'll submit it together in class or something. But yeah, that's fine. Just focus on problems at 4 and 5.
Okay, thank you.
Yep.
Yeah.
Wait, Professor, before we go, I actually had a question.
Sure.
So I was looking at my grades, right? And it said that
something's not right.
Oh yeah, for practice midterm 1, it says I got 0 points out of 32, even though I recall doing it.
Oh, okay. I'll fix that. Don't worry. That was,
Okay.
you know, when Lumen was, well, Lumen's still giving me some problems, but I think it's actually Blackboard's problem. Yeah, but let me just go in it right now. So it looks like you're doing well on the practice midterm. Okay, so I'll fix that right now and you'll see it updated soon, okay?
Got it. Okay. Great. Thank you so much.